Thermal mass flow meters. Sensor design is key to stability, accuracy, and in situ validation. Industrial thermal mass flow meters comprise a family of instruments for precision measurement of total mass flow rate of gases in the pipes and ducts. Standard accuracy is 1% of full-scale flow, but recent innovation, as with Sierra's 4-sensor quadratherm thermometer, has pushed accuracy to 0.5% of reading, rivaling that of Coriolis meters. In addition to accuracy, thermal flow meters have become extremely popular due to high turndown, up to 1,000 to 1, giving the ability to measure very low flows up to very high flows with the same instrument. Since they are rugged and reliable, have no moving parts, are easy to insert via hot tap, have negligible pressure drop, and offer an economical solution to large diameter pipes and ducts, thermal technology has been rapidly adopted over the last decade. Today, thermal mass flow technology is widely used in a broad range of industrial process control applications spread across global industries. The basic physics of thermal dispersion mass flow meters is attributed to Louis Vaisseau-King, who in 1914 published his famous King's Law, mathematically describing heat transfer in flows, using a heated wire immersed in a fluid flow to measure the mass velocity at a point in the flow. King called his instrument a hot wire anemometer. Fragile and delicate, hot wire anemometer technology of the time was a simple platinum wire wound around a glass mandrel exposed in the flow. This made them extremely prone to breakage. It wasn't until much later, when innovators like Dr. John George Olin, founder of Sierra Instruments, saw the rapidly growing need in industry for a truly industrial thermal hot wire anemometer. To make a thermal flow sensor truly industrial strength, Dr. Olin pioneered the innovation of an all-metal clad thermal sensor in the early 1980s, winding platinum wire around a ceramic mandrel and placing it inside a metal sheath called a thermal well. The problem was that the air gaps between the thermal well and the platinum wound mandrel needed to be filled to assure stable heat transfer. This was the key to assuring an accurate and stable thermal mass flow meter. To do this, he filled the air gap with a potting compound of conductive epoxy, also called thermal grease or cement. This type of sensor is known today as a wet sensor. This wet design proved that it did work, but had its weaknesses. Wet thermal sensor design, because of the organic potting cement used, would shift and crack over time, causing unwanted sensor drift, resulting in a gradual degradation of flow measurement accuracy. Today, wet thermal sensors are used by all industrial thermal sensor manufacturers on the market, with one exception, and that is Sierra. Sierra never stopped improving the technology, knowing that wet sensor drift problems must be solved. After all, by its very principle of operation, a thermal sensor is heated and cooled over time, expanding and contracting the cement inside the sensor, making it crack, settle, and shift from its original state. Think of freshly poured cement on a sidewalk. Eventually it hardens, and then it usually cracks, shifts, and settles as it is heated by the sun, and then cools again, repeating this cycle over and over. This is what is happening inside a wet thermal sensor. Dr. Olin believed there had to be a better way. He needed to get rid of all cements to make the most stable thermal sensor in the world. After many years of experiments and testing, the answer finally revealed itself. On March 9, 1999, Dr. Olin patented a breakthrough thermal sensor design. Like other thermal mass flow sensors, it was made of a platinum resistance temperature detector wire wound around a ceramic mandrel. But this is where the similarities ended. Through a proprietary, highly controlled manufacturing process, a metal sheath is tightly formed on the mandrel and wire assembly to be in such intimate contact that no air gaps exist and no organic filler cements are needed. This new sensor was literally all metal. In contrast to wet sensor design, this innovative cement-free sensor is known as a dry sensor. It is patented by Sierra and is brand named DrySens. In the illustration, you can physically see the difference in diameter on the Sierra velocity sensor where it was tightly formed around the mandrel. No other manufacturer will have this distinct signature look. All materials used to make the DrySens sensor were selected such that their coefficients of thermal expansion are approximately the same. The added benefit is that they expand and contract at the same rate, further assuring rock-solid stability. Because the all-metal DrySens sensor is so rugged, reliable, and stable, Sierra has backed quality claims to be the only company in the industry to offer a lifetime warranty on their thermal sensor. The DrySens sensor has been in use on all Sierra thermometers since its invention in 1999, and in 2009 was named the best-selling thermometer in North America by Flow Research Incorporated of Boston, Massachusetts. So, when evaluating thermal mass flow meters for in situ calibration validation capability, be aware that sensor drift will create false positives, reducing the reliability of the validation. Sierra's motto has always been, don't recalibrate, validate. Be careful. The problem with in situ validation methods is that they only measure the characteristics of the internal sensor windings and do not address sensor drift. The big question is, how can you validate a sensor that will drift out of spec due to the very nature of its mechanical design? The resistance of the platinum wire shouldn't change, and the current running through the sensor might be the same, both of which would validate OK. This is a false positive, as the drift inherent in a wet sensor design would remain unseen. Sierra's DrySens all-metal no-drift sensor has a big advantage during in situ calibration validation. With Sierra's all-metal DrySens velocity sensor, you have the mechanical design confidence that there will be no drift and that in situ calibration validation is indeed actually valid. For accurate and repeatable gas mass flow measurement down to the last molecule, choose thermal mass flow technology. Experience our passion for flow. For more information, go to www.sierrainstruments.com, the global leader in flow instruments.